Hi everyone, welcome to your first content video. In this video, you're going to learn about set notation and interval notation. And we're starting with this because we will use this notation throughout the course. All right, so let's get into it. We're going to start with sets. A set is a collection of objects. Each object in a set is called an element. A set is named using a capital letter. And is written with its elements listed in braces, or more specifically, curly braces. So let me give you some examples. I'm going to call our first set, set A. And in this set, I'm going to use numbers for the elements. So we'll just make the elements 1, 2, 3, 4, and 5. So set A consists of the elements 1, 2, 3, 4, 5. Now let me give you an example where the elements are not numbers. I'm going to call this set set C. And I'm going to let the elements be shirts, pants, shoes, belts, sweaters. So set C could represent the items in your closet, let's say. All right, next we're going to look at some of the symbols that we use with set notation. So the first symbol we use for the empty or null set, and this would just be a set that has no elements. Okay. All right, our second symbol, which kind of looks like a sideways U, or maybe a C, but probably more like a sideways U. This symbol stands for the subset. So we would read this as set A is a subset of set B. Okay, our next symbol, which does look like a U, stands for the union. So again, we would read this as the union of set A and set B. You can also think of the union as or, so we'd be looking for the elements in set A or set B. And then our next symbol looks like an upside down U, and it stands for the intersection of set A and set B. You could also think of that symbol as the word and. So in this case, we're looking for the elements in set A and set B. And then our last symbol, which looks like an E, stands for element of. So when you see this symbol, you would read it as is an element of. You might see something like this, which would be read 3 is an element of set A. Okay, let's look at some examples using these symbols. We're going to start with some true or false questions. We're given two sets here. Set A equals 1, 2, 3, 4, and 5, and then in set B, the elements are 4 and 5. So true or false? Number 1, 3 is an element of set A. Well, sure enough, we have a 3 in set A, so that is true. Number 2, 3 is an element of set B. Well, that's false because we don't have a 3 for set B. All right, number 3, B is a subset of set A. Well, that is actually true because B consists of the elements 4 and 5, and 4 and 5 are in fact elements of set A, so set B is a subset of set A. Okay, let's look at it the other way around. Set A is a subset of set B. Well, that would be false because we do not have 1, 2, 3, 4, and 5 in set B. Okay, now 5 and 6 are not true or false. For number 5, we're being asked to find the union of set A and set B. And remember, in that case, we're looking for the elements in set A or set B. You can also think of union as just bringing the two sets together. So this would consist of the elements, basically, that are in both sets. So the union of set A and set B would be 1, 2, 3, 4, and 5. Okay, now number 6, here we're looking for the intersection of set A and set B. So here we're looking for elements that are in set A and set B. And so in that case, the two numbers that are in both sets are 4 and 5. You can also think here that you're looking for the overlap, okay? I like to think of the union, like in number 5, as you're just bringing the two sets together. You're joining the two sets and basically listing all the elements in both sets. And then for number 6, the intersection, I think of as the overlap. You know, what are the elements that are in both sets? Okay. Now, let's talk about the real number system and sets of real numbers. So in this class, we will only use real numbers, and you might be thinking, okay, well, what other kind of number would we use? The other kind of number would be an imaginary number. And you know, definitely learned about imaginary numbers in Algebra 2. So the good news for you is that we will basically stick to real numbers, so no imaginary numbers. All right, so you guys, under the real number system, we have subsets of numbers, and I'm actually going to start at the bottom and kind of take you through a little history of numbers. You know, numbers came about because there was a need to count things. And so usually when you're counting how many of something, you start with 1. You know, if I don't know, counting how many letters are in a word, you know, I would start with 1, 2, 3, 4, 5, like how many letters are in the word number. You know, in that case, I would start at 1. There's 1, 2, 3, 4, 5, 6 letters in the word number. So we call our first subset of numbers natural or counting numbers. Sometimes you'll hear these referred to as counting numbers. And so this subset of numbers, we actually represent the subset with a capital N for natural numbers. And so this set of numbers starts at 1 and then goes up as if you're counting, and of course keeps going. Well, then over some time, people realized that we needed a way to represent nothing. What if there's nothing to count? And that led into the number 0. And so your subset of whole numbers basically just adds 0 to the subset of natural numbers. Now we represent whole numbers with a capital W. And so this subset of numbers just starts at 0, 1, 2, 3, dot, 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 because it keeps going. All right, well then over some time, people realized there was a need for negative numbers. And so if we add the negative numbers now, we have what we call the subset of integers. Now, the subset of integers we actually represent with a capital Z. This comes from the German word for number or numbers, which is Zahlen. I'm probably not saying it 100% right, but pretty close. But anyway, if we just add negative numbers to our list, then we have the subset of integers. Okay, now notice that natural numbers, whole numbers, and integers are all under the subset of rational numbers, because all of these subsets of numbers are considered rational numbers. Now, what do we mean by rational numbers? Rational numbers are numbers that can be written as a fraction, okay? Because rational numbers can be written as a fraction, we actually use a Q for this subset of numbers. Q meaning quotient, because a fraction bar means to divide. So rational numbers basically include the natural numbers, the whole numbers, the integers, but also include the numbers in between, the fractions, the decimals, okay? Now, obviously a fraction is a quotient, so rational numbers would include proper fractions, improper fractions. I'm just giving you some examples here. Mixed numbers, and also decimals. But the decimals have to either end or have a pattern, meaning they repeat. So a decimal that ends would be something like 2.5. That decimal can be converted to a fraction, as a fraction is 5 divided by 2. Or fractions that repeat. So maybe like 1.333333. The 3's go on forever, and so we usually just put a bar above what repeats. Okay, so if the number is not a rational number, okay, which also includes the integers, the whole numbers, and the natural numbers, then that means that the number is an irrational number. So the only type of number we've left out are what we call irrational numbers. Irrational numbers are those decimals that never end and have no pattern, meaning they don't repeat. Okay, so I usually say irrational numbers are decimals that never end and never repeat. So what are we talking about here? Well, one irrational number that you're probably very familiar with is pi. We talk very often about the fact that pi is approximately 3.14, but it actually is a decimal that never ends and never repeats. There is another popular irrational number called e that we'll talk about a lot. And also, irrational numbers appear when you're finding square roots. So if you try to take the square root of a non-perfect square, like 2 for instance, square root of 2 is a decimal that never ends and never repeats. So our subset of irrational numbers, we actually use a capital I to represent the irrational numbers, which is why we use a Z for integers, because I was already taken. And then if we put all these subsets of numbers together, we get the set of real numbers, and we actually use a capital R for our set of real numbers. And so your real numbers just include irrational and rational numbers. Okay. All right, so just to practice with these subsets of numbers, of real numbers, in these 4 examples, our goal is to list all of these sets of numbers that this number belongs to. So for instance, 4, I'm going to go back. 4 is a natural or counting number. It's also a whole number. It's also an integer. It's a rational number, and of course, it's a real number, because all of these are real numbers, unless it's imaginary. So we would want to list all of those subsets. It's a natural number, a whole number, an integer, a rational number, and a real number. So this is a little bit easier if you kind of start from the bottom and go up. So let's look at number 2, -5. So -5, because it's a negative number, -5 is an integer. which means it's also a rational number and it's a real number. So -5 is an integer, a rational number, and a real number. All right, 3/5, which is a fraction, means it's a rational number, and of course, it's also a real number. Okay, square root of 10, that's where you're taking the square root of a non-perfect square. That's going to result in an irrational number, a decimal that never ends and never repeats. But of course, it is also a real number. Okay, the next notation we're going to look at is called set builder notation. And we won't use set builder notation that often, but it's good for you to be familiar with it because you often see it used like in textbooks or, you know, whatever you might be using to practice, be it a website or whatever. We often see set notation. So I don't want you to see it and get confused because you don't understand it. But it's also a way to represent a set of numbers when it's impossible to list all the elements in the set. Okay, so that's another reason we might use set builder notation. Okay, so notice we still use the curly braces. The way that you would read this is the set of all x such that -3 is less than or equal to x and x is less than or equal to 16. X is an element of the set of integers. Okay. So let's look at some examples. So here we want to describe the set of numbers using set builder notation. So honestly, you just kind of repeat that same setup. So you always start with the set of all x such that, and then if you're not given an inequality like we were in number 2, you just want to take these numbers and write them as an inequality. So it's looking like the numbers in this set are greater than or equal to 2, but the numbers I'm noticing are also integers, so I can say x is an element of the set of integers. You could also, instead of a z for integer, you could have used n for natural numbers, or you could have used a w for whole numbers. I just chose to use z for integers. Okay, for number 2, again, we'll just start with our curly brace, x such that x is greater than -17. That was easy, we're just repeating the inequality. But guys, if we're saying x is greater than -17, then that would include all numbers greater than -17, which would mean the irrational, the rational. So in this case, we would have to say x is an element of the set of real numbers. Okay, and then number 3, and we'll start with our curly brace. X, the set of all x such that, and this time it looks like x is greater than or equal to 0, and that x is an element of, and I think I'll use a w this time, why not? X is an element of the set of whole numbers. Since we started with 0, I thought we would use whole numbers as the subset. Okay. All right. Next, we're going to look at interval notation, and actually, this type of notation we will use quite often. So interval notation uses inequalities to describe subsets of real numbers. Now, you should be familiar with inequalities, you know, from your previous algebra courses. So you can think of interval notation as just another way to write an inequality. So we have 2 different types of intervals. We have bounded and unbounded. So bounded intervals, it just means that you have 2 endpoints. So A and B are the endpoints, where an unbounded interval only has 1 endpoint. And then basically the inequality continues forever in either direction. One thing that can be helpful initially, if you're not used to interval notation, is to graph the inequality on a number line. Usually when you learn about solving inequalities in algebra, you're often asked to graph the solution on a number line. And you might recall that if the inequality sign is, let's say, less than or greater than, you would use an open circle on the number line. And if the inequality is less than or equal to or greater than or equal to, you would use a closed circle on the number line. Interval notation is similar. For an open circle, we would use parentheses, and for a closed circle, we would use a bracket. Okay. Now, keep in mind there's some meaning here in relation to that inequality or subset of numbers. If you use a bracket or a closed circle, that means that we include the endpoint in that interval. And if we use parentheses, then we're saying that we're not including that endpoint in the interval. Okay. So let me show you what I mean. If we were given the inequality a is less than or equal to x and x is less than or equal to b, if you were to graph that on a number line, you would have used closed circles for a and b. And so in interval notation, notice we just use a bracket. So it's just bracket a, comma b, bracket. Okay. All right, for our next inequality, we have a is less than x and x is less than b. So in this case, we would use open circles for a and b. And so then in interval notation, we would just use parentheses. So in this case, we would not include a and b in the interval. We would include values close to a and b, but not those exact values. All right, our next inequality is a is less than or equal to x and x is less than b. So in this case, we use a closed circle on a and an open circle on b. So in interval notation, we would use a bracket on the a and parentheses on the b. Okay, and then our next inequality is a is less than x and x is less than or equal to b. So that would be an open circle on a and a closed circle on b, meaning in interval notation, we would use parentheses on a and then a bracket on b. Okay, for our unbounded intervals, this is where if you were to graph the inequality, it's going to continue forever to the left or to the right. So for instance, for x is greater than or equal to a, we would use a closed circle on a, but then your inequality would go forever to the right, meaning it's going to infinity. Because keep in mind, on your number line, 0 is in the middle. You know, if we go to the left forever, we're going to negative infinity. If we go to the right forever, we're going to infinity. Although keep in mind, we usually read a number line from left to right. So like in all of these examples, a would be less than b. Okay. All right, so notice for x is greater than or equal to a, we would use a bracket on the a. Now with infinity, we always use parentheses because infinity is really a concept. It means that those numbers are going on forever. And so we can't really include infinity in our interval. So we always use parentheses for infinity. Okay, our next inequality is x is greater than a. So if I were to graph this on my number line, I'd use an open circle on a. And again, my arrow would continue to the right forever. And so in interval notation, we would use parentheses on the a, comma, infinity, and then parentheses on infinity. All right, let's look at x is less than or equal to a. So this time, if I were to graph on a number line, I'd use a closed circle on a, but my arrow would go to the left. And so when you write this in interval notation, you start with negative infinity, comma A, and then a bracket on the A that coincides with the closed circle. Of course, that also means we're going to include A in that interval. All right, and then our last one is x is less than A. So in this case, we use an open circle on A. The arrow would go to the left forever. So in this case, again, we'd start with negative infinity, comma A, but then parentheses on the A, meaning we're not including A in that interval. And you guys, A and B, you know, those will be actual numbers when you write interval notation. So let me show you some examples. And I think you'll see this is pretty easy. We want to write each set of numbers using interval notation. So number one, given the inequality, -2 is less than or equal to x, and x is less than or equal to 12, in interval notation, this is how easy it is. Bracket -2, comma 12, bracket. I'm using brackets because the inequalities were less than or equal to. Okay, number two, x is greater than -4. In interval notation, that would be parentheses, -4, comma, infinity. And again, if you're having trouble with this, I would say graph that inequality. For instance, we would have an open circle on -4, but then an arrow going to the right, because x is greater than -4. All right, number three, x is less than 3, or x is greater than or equal to 54. So in this case, we're going to have to write two intervals, okay? So for x is less than 3, now keep in mind, if I were to, let's say, graph this as an inequality, it would look like this. So we got to start with the negative infinity, okay? So it'd be negative infinity, comma 3, parentheses, because it would be an open circle. Or, so that's where we're going to use that U symbol, x is greater than or equal to 54. So in this case, it would be a closed circle on the 54, and the arrow would go to the right, to infinity, so it would be a bracket 54, comma, infinity. And parentheses, of course, we always use parentheses for negative infinity and infinity. Okay, I thought since I graphed those two, I might as well graph this one as well, so you can see, you know, how it corresponds to the interval notation. Okay, now let's look at number 4. This is a notation we will also use. We would read this as x is not equal to 2. So if we're just eliminating one value, let's say that we were graphing this on our number line, and here's 2. It would end up being an open circle on 2, and then arrows going in both directions. So in interval notation, we do have to write two intervals. We would start with negative infinity to 2, parentheses, because we don't want to include the 2, union, or the U, meaning 4. And then we have to write an interval for the other arrow, which is from 2 to infinity. So by breaking this up into two intervals and using parentheses on the 2, we're saying that we're just not including the 2. Okay, so basically x cannot equal 2. That's the only one number we're eliminating from this set of numbers. Okay. All right, so you guys, we'll definitely practice this in class some more. And I would like to thank you for watching, and have a good night.